What if, as you woke, the world had already shifted into an ice age? Could you feel the first breath of cold in the air? Or would it be hidden, invisible, written in ice crystals too small to see? We begin by asking how sudden or silent such a transformation could be. The morning light feels different when you consider this possibility. Not sharper, not dimmer, but somehow more fragile, as if the photons themselves carried a whisper of what's coming. You step outside and breathe, and perhaps, just perhaps, there's something in that breath that wasn't there yesterday. Something older, something patient. Science tells us that ice ages don't arrive like storms. They creep in over centuries, millennia, each winter lasting a few days longer, each summer retreating a few degrees cooler, until one day the snow that falls in October never melts. But what if we're wrong? What if the trigger, when it comes, moves faster than we imagine? Consider the Younger Dryas, that mysterious cold snap that struck Earth 12,900 years ago. In perhaps as little as a decade, temperatures plummeted, glaciers advanced, and the world that early humans knew simply changed. The cause remains debated, a comet impact perhaps, or the sudden collapse of ice sheets redirecting ocean currents. But the speed was undeniable. The Earth, it seems, can shift between climates as quickly as a sleeper turns in bed. So you wake, and the air tastes different. Not colder yet, but carrying within it the memory of cold. The trees outside your window stand as they always have, but something in their stillness suggests they're listening for the first whisper of snow that will never melt, the first frost that will deepen rather than fade. This is not about fear. Fear is too immediate, too personal. This is about wonder at the scales of time and change that dwarf our daily concern. It's about recognizing that we live in a brief pause between ice ages, in an interglacial moment that has lasted 11,700 years, a blink in geological terms. The Pleistocene epoch, which began 2.6 million years ago, has been defined by its rhythm of advancing and retreating ice. We are not living after the ice age, we are living between them. The mechanisms are already in motion, invisible and patient. Solar radiation changes as Earth wobbles through space. Ocean currents shift with microscopic precision. Atmospheric chemistry dances to rhythms we barely comprehend. The triggers are not dramatic, they are subtle, accumulating, waiting for the moment when small changes cascade into transformation. You might not notice the beginning. The first sign might be nothing more than snow lingering a few days longer in the mountain, alpine meadows staying white past their usual thaw, permafrost spreading its underground fingers deeper into soil that has been soft for millennia. These changes would appear in scientific papers before they appeared in your daily experience. But once begun, once the Earth's albedo, its reflectivity begins to increase, as more white surfaces reflect sunlight back to space, the process could accelerate beyond our control. We live in cities that assume tomorrow will be like today. Our agriculture depends on stable growing seasons. Our coastlines are shaped by current sea levels. Our entire civilization is calibrated to the narrow band of temperatures and weather patterns we call normal. But normal in Earth's longer memory includes ice sheets 2 miles thick covering what is now New York City. Normal includes sea levels 400 feet lower than today, exposing land bridges between continents, creating landscapes we can barely imagine. So what if tomorrow froze? Not the day after today. That tomorrow is safe, protected by thermal inertia and the vast heat capacity of our ocean. But the tomorrow of our species, the tomorrow of our children's children's children, that tomorrow stands at the edge of probability, waiting. And in that waiting, there is something both humbling and beautiful about recognizing our place in Earth's longer story. The question is not whether another ice age will come. The question is whether we will recognize its beginning, whether we will understand the whispers before they become shouts, whether we will have the wisdom to adapt to changes that unfold on timescales longer than empire. And as you stand in that different morning light, breathing that subtly different air, you might wonder, are we already listening to its first quiet song? The ice remembers everything, every breath of ancient wind, every grain of volcanic dust, every molecule of air that danced through skies we will never see. Glaciers are libraries of time, preserving air bubbles, dust and isotopes that whisper of forgotten climates. And as we learn to read these frozen stories, we glimpse not just our past, but the shape of our possible tomorrow. Deep in the heart of Antarctica, Scientists extract cylinders of ice like pulling memories from the Earth's dreams. Each layer tells a story. This stripe of blue-white ice fell as snow when mammoths walked across land bridges. This bubble of ancient air was exhaled by forests that existed before humans learned to speak. The ice core speaks in ratios, oxygen isotopes that reveal temperature, atmospheric carbon that charts the breathing of ancient ecosystems, volcanic ash that marks catastrophic years when the sky turned dark. But these are not just data points. They are moments of intimacy with deep time. When you hold a piece of ice that formed when the pyramids were built, you are touching a messenger that has waited centuries to deliver its news. The ice carries within it the exact atmosphere that surrounded Cleopatra's breath, the chemical signature of air that filled the lungs of dinosaurs, the molecular memory of climates so different from ours that they might as well be alien worlds. The Greenland ice sheet holds 10,000 years of weather reports written in a language of crystal and chemistry. Scientists have learned to read the handwriting. Rapid changes marked by sudden shifts in isotope ratios, gradual transitions recorded in slowly changing ice composition, catastrophic events preserved as dark layers of ash and debris. The ice sheet is 2 miles thick in places, each layer representing another year, another season, another moment in the Earth's long conversation with the sun. What emerges from this frozen library is a story of instability that challenges our assumptions about climate. We tend to think of change as gradual, but the ice tells a different tale. It speaks of the Dansgaard-Oshia events, rapid climate oscillations during the last ice age when temperatures could shift by 15 degrees Fahrenheit in a matter of decades. It preserves evidence of Heinrich events when massive armadas of icebergs carved from ice sheets and sailed south, dropping debris across the ocean floor and temporarily shutting down the circulation systems that regulate Earth's temperature. The ice remembers the medieval warm period, when Vikings farmed in Greenland and wine grapes grew in England. It holds within its frozen archive the Little Ice Age when the Thames froze solid and crop failures sparked social upheaval across Europe. These are not ancient history, they are recent variations in Earth's climate system, reminders that the stability we consider normal is actually quite rare in the longer record. But perhaps most haunting are the air bubbles trapped in ancient ice. These microscopic time capsules contain samples of atmospheres from thousands of years ago. When scientists extract and analyze these ancient air pockets, they are literally breathing samples of the atmosphere that surrounded our ancestors. The carbon dioxide levels, the methane concentrations, the trace gases that reveal the state of ancient ecosystems, all preserved in perfect frozen suspension. The ice tells us that our current atmosphere is unprecedented in the record it preserves. The sharp spike in greenhouse gases since the Industrial Revolution appears in the ice cores as a dramatic departure from natural pattern. But it also reveals that rapid atmospheric changes are not unprecedented. They simply usually coincide with major transitions between climate states, the kind of transitions that reshape continents and redefine what we mean by normal. There is something profoundly moving about this frozen memory. Ice forms from snow that fell during moments of Earth's history we can only imagine. Snowflakes that danced in ancient storms became compressed into layers that now tell us about civilizations that rose and fell, about ecosystems that flourished and vanished, about the slow pulse of ice ages advancing and retreating across the continent. The isotope ratios preserved in ice cores reveal not just temperature, but the sources of ancient precipitation. Scientists can trace where ancient snow originated, following the chemical signatures like fingerprints that reveal whether moisture came from nearby oceans, or traveled vast distances through the atmosphere. They can detect the timing of seasonal cycles from thousands of years ago, reading the annual layers like tree rings to understand how ancient seasons unfolded. And the ice continues to remember, continues to record, even as it melts. The edges of ice sheets are retreating, carrying with them the oldest layers of this frozen archive. As ancient ice melts and flows to the ocean, it takes with it irreplaceable records of Earth's climate history. We are simultaneously reading this library and watching parts of it dissolve, creating an urgency to decode its messages before they return to the sea from which they came. Yet in this melting there is also revelation. As permafrost thaws and ancient ice disappears, it sometimes releases even older memories. Organic matter that has been frozen for tens of thousands of years. Perfectly preserved samples of ancient life that suddenly find themselves in our modern world. Seeds that sprout after millennia of dormancy. DNA that tells stories of extinct ecosystems. Chemical signatures of atmospheres so ancient they predate our species entirely. The ice sheet memory extends beyond Earth's surface. Scientists have found cosmic dust in ice cores, tiny particles from space that settled in ancient snow, carrying with them information about solar activity and cosmic events that influenced Earth's climate. Even meteoric debris appears in the frozen record, marking moments when our planet intersected with debris from ancient cosmic collision. And yet if this much can be preserved in ice, if every breath and grain of dust can be archived in frozen layers, what else might the Earth remember in ways we haven't yet learned to read? Ice ages are not accidents but patterns guided by the slow turning of Earth's orbit and tilt. And as we drift through understanding of Milankovitch cycles, we discover how celestial rhythms tune our climate like a cosmic metronome, playing songs that last longer than species, longer than continents, longer than the memory of stone itself. Imagine Earth as a dancer, spinning through space in movements so vast and slow that entire civilizations rise and fall between one step and the next. The dance has three primary motions: the wobble of Earth's axis like a spinning top slowing down, the tilt of that axis changing like a dancer, leaning into and away from the light, and the stretch and squeeze of Earth's orbit around the sun like breathing, that takes 100,000 years for each inhale and exhale. Milutin Milankovitch, a Serbian mathematician, first calculated these celestial rhythms in the early 20th century. Working with nothing more than pencil and paper, he mapped how Earth's orbital variations would affect the distribution of sunlight across the planet's surface. His calculations predicted ice ages with mathematical precision, though it would be decades before ice core data would prove him right. The elegance of his discovery lies not just in its accuracy, but in its revelation of Earth as part of a cosmic clockwork, subject to gravitational forces and celestial mechanics that operate on timescales beyond human comprehension. The eccentricity cycle stretches across 100,000 years, during which Earth's orbit shifts from nearly circular to noticeably elliptical, and back again. When the orbit is more elliptical, the difference between Earth's closest and farthest approach to the Sun becomes more pronounced, affecting the intensity of seasons. Currently we experience our closest approach to the Sun during Northern Hemisphere winter, which moderates the cold. But this relationship shifts over time, sometimes amplifying seasonal differences, sometimes diminishing them. The obliquity cycle unfolds over 41,000 years as Earth's axial tilt varies between 22.1 and 24.5 degrees. Currently we sit at 23.4 degrees, but this angle is slowly decreasing. When tilt is greater, seasons become more extreme, summers hotter, winters colder. When tilt is smaller, seasons moderate, and this moderation can be crucial for ice sheet formation. Cooler summers in the high northern latitudes mean that winter snow doesn't completely melt, allowing ice sheets to grow year after year, century after century. The precession cycle completes every 26,000 years as Earth's axis wobbles like a spinning top. This wobble changes which hemisphere is tilted toward the Sun during different parts of Earth's orbit, effectively shifting the timing of seasons. Sometimes Northern Hemisphere summer coincides with Earth's closest approach to the Sun, making summers there particularly warm. Other times Northern Hemisphere summer occurs when Earth is farthest from the Sun, leading to cooler conditions that favor ice sheet growth. But these cycles don't operate in isolation. They weave together in complex patterns, sometimes reinforcing each other, sometimes cancelling each other out. When all three cycles align to reduce summer insolation in the Northern Hemisphere, ice sheets begin their slow advance. Snow that doesn't melt in summer accumulates year after year, compacting into ice, reflecting more sunlight back to space, cooling the planet further, allowing the ice to advance even more. It's a feedback loop written in orbital mechanics and carved in ice. The beauty of this system lies in its inevitability and its patience. These cycles have been operating for millions of years, indifferent to the life they nurture or challenge on Earth's surface. They operated when the first mammals scurried between dinosaur feet, when the first flowers bloomed, when the first humans looked up at stars and wondered about their place in the cosmos. They will continue operating long after our species has either transcended or succumbed to the changes they bring. The geological record reveals their signature across deep time. Ice age cycles are preserved in marine sediments, where the shells of tiny organisms record ancient ocean temperatures and ice volumes. They're written in terrestrial deposits, where alternating layers of glacial and interglacial sediments mark the advance and retreat of continental ice sheets. They're carved into landscapes, where glacial valleys and moraines map the boundaries of ice sheets that existed hundreds of thousands of years ago. What makes these cycles particularly fascinating is their role as a pacemaker for evolution. Species adapt not just to immediate environmental pressures,
but to the rhythmic changes imposed by orbital cycles. Ice ages fragment habitats, create corridors for migration, drive some species to extinction while providing opportunities for others. The human lineage itself bears the signature of ice age cycles. Our ancestors evolved during a period of increasing climate instability, possibly developing the cognitive flexibility that would eventually lead to culture, language, and civilization. The Milankovitch cycles also interact with other Earth systems in ways that amplify or dampen their effects. Ocean circulation patterns respond to orbital forcing, redistributing heat around the planet in ways that can accelerate or delay ice age transition. Atmospheric carbon dioxide levels fluctuate in harmony with ice age cycles, though the relationship is complex. Sometimes ice ages drive atmospheric changes, sometimes atmospheric changes drive ice ages, and sometimes they dance together in feedback loops that scientists are still working to understand. Currently we exist in what should be a cooling phase according to Milankovitch calculation. The configuration of Earth's orbital parameters suggests we should be slowly heading toward the next ice age, but human activities have overwhelmed the subtle orbital forcing with dramatic increases in greenhouse gas concentration. We are living through a moment when human influence on climate is stronger than astronomical influence, a situation that is probably unprecedented in Earth's history, yet the cycles continue. Earth's orbit still wobbles and stretches and tilts according to the same gravitational laws that have shaped climate for millions of years. The next ice age has not been cancelled, merely delayed. Some calculations suggest that without human influence, the next ice age might begin with human influence it might be delayed for hundreds of thousands of years, but eventually inevitably the orbital cycles will reassert their influence, and ice will advance again across continents that have forgotten the weight of glacial silence. There is something both comforting and unsettling about this cosmic clockwork. Comforting because it reveals an underlying order to climate change, predictable patterns that operate according to physical laws we can understand and calculate. Unsettling because it reminds us that Earth's habitability operates according to rhythms much larger than human timescales, rhythms that will continue long after we have either adapted to their demands, or become another layer in the sedimentary record of extinct species. The dance continues, Earth spinning through space, leaning into and away from stellar light, breathing in orbital rhythms that measure time in millions of years. And in this dance, ice ages and interglacials are not disasters and reprieve, but simply the natural rhythm of a planet moving through space, following gravitational music written in the language of celestial mechanics, playing songs that began before life existed and will continue long after the last glacier has melted and the last ice age has ended in the distant glow of our sun's final year. But if celestial rhythms can carve continents and drive evolution, what happens when those same rhythms begin to reshape landscapes we call home? Mountains shaped like sculpture, valleys carved by vanished rivers of ice. We imagine how an advancing sheet of frozen weight would once again transform our familiar lands into forgotten shapes of silence, where every hill and hollow speaks of forces, so patient they measure progress in millennia rather than moments. The land remembers ice, even now thousands of years after the last glaciers retreated from most of North America and Northern Europe. The landscape bears their signature. The gentle rolling hills of the American Midwest are moraines, piles of rock and sediment, pushed ahead of ice sheets like snow before a plow. The Great Lakes are scars left by glacial gouging, basins carved so deep that they hold 6 quadrillion gallons of fresh water, a legacy of ice that disappeared before the first pyramids were built. But these remnants are just whispers of what ice can do. To understand the full power of glacial transformation, we must imagine landscapes being born from silence, the slow, inexorable advance of ice sheets that turn mountains into smooth domes, carve valleys deeper than skyscrapers are tall, and transport boulders the size of houses across hundreds of miles as casually as wind carries leaves. Consider the Finger Lakes of New York, those 11 parallel valleys that stretch north to south like the impression of a giant hand pressed into the earth. Each lake fills a valley carved by glacial tongues that advanced and retreated multiple times over millions of years. The ice didn't just scrape the surface, it gouged deep channels into bedrock, some extending hundreds of feet below current sea level, creating basins that would later fill with water when the glaciers finally retreated. This is the artistry of ice, transformation through patient pressure. A glacier moves imperceptibly slowly, perhaps a few feet per year, sometimes less, but it moves with the weight of mountains. Ice accumulates in highland areas, compacting under its own weight until it becomes dense enough to flow like very slow liquid. As it flows, it incorporates rock and debris, becoming a river of frozen sandpaper that can plane down granite, carve through limestone and reshape entire drainage systems. The process begins subtly. Snow accumulates in areas where summer melting cannot keep pace with winter accumulation. Year after year the snow deepens, compresses, recrystallizes into firn, then into glacial ice. When the ice reaches sufficient thickness, perhaps 100 feet, its own weight causes it to begin flowing outward from its center of accumulation. This flow is almost invisible, measurable only with sensitive instruments, but once begun it becomes unstoppable. As glacial ice flows downhill, it plucks rocks from the landscape, freezing to bedrock, and then pulling away chunks of stone as it moves. The ice becomes studded with rock fragments of all sizes, from fine sediment to house-sized boulders. This debris-laden ice then acts like a massive file, grinding against the bedrock beneath it, polishing some surfaces to mirror smoothness, while gouging deep scratches called striations that reveal the direction of ice flow. The landscapes that emerge from beneath retreating ice sheets are alien in their freshness. Valleys carved by glaciers have a distinctive U-shaped profile, unlike the V-shaped valleys carved by rivers. Glacial valleys are often deeper than they are wide, with straight walls that rise hundreds or thousands of feet from flat floors. These valleys can be so deep that they create their own weather patterns, channeling winds and creating microclimates that persist long after the ice has gone. In mountainous regions, glaciers carve landscapes of almost supernatural beauty. Cirques, bowl-shaped depressions where glaciers begin, are carved into mountainsides like enormous amphitheater. When multiple cirques form on different sides of the same peak, they can carve the mountain into sharp ridges called arete, or even into knife-edge peaks called horn. The Matterhorn in the Alps is perhaps the most famous example of a glacial horn, its distinctive pyramid shape carved by glaciers that approached from all sides. Glacial lakes form in these carved landscapes through several mechanisms. Some fill cirques creating tarns, small deep lakes nestled in high mountain bowls. Others form when glaciers dam natural drainage, creating vast temporary lakes that can hold thousands of cubic miles of water. When these glacial dams fail, they unleash floods of almost unimaginable power, capable of carving canyons in a matter of days or hours. But perhaps the most remarkable aspect of glacially carved landscapes is their silence. These are places shaped by forces so slow that they operate below the threshold of human perception, yet so powerful that they can move mountains. The silence of glacial landscapes is not the absence of sound, but the presence of deep time made visible. Standing in a glacially carved valley, surrounded by walls of stone polished smooth by ice that disappeared thousands of years ago, you are witnessing the results of processes that operated with the patience of geology and the persistence of gravity. The sediments carried by glaciers create their own landscapes. Terminal moraines mark the farthest advance of ice sheets, creating natural dams that often hold back lakes or redirect rivers. Drumlins, elongated hills sculpted by flowing ice, dot formerly glaciated regions like sleeping whales, all oriented in the direction of ancient ice flow. Eskers, serpentine ridges of sand and gravel, mark the courses of rivers that flowed beneath ice sheets, depositing their sediment load in tunnels that were later exposed when the ice melted. These glacially shaped landscapes possess a particular quality of light and space that seems to expand the horizons of human perception. The scales are so vast, the process is so fundamental, that they invoke a kind of geological sublime. To stand on a summit surrounded by glacially carved peaks is to see the earth as a work of art, created by forces that operate on time scales, longer than species, longer than continents, longer than anything in human experience except the stars themselves. The ice that carved these landscapes also transported life, seeds, spores. Even small animals could be carried vast distances in glacial ice, creating founder populations in newly exposed territories as the glaciers retreat. The colonization of landscapes emerging from beneath ice sheets represents one of the most dramatic examples of ecological succession on Earth. As life gradually transforms bare rock and glacial sediment into complex ecosystems, some glacially carved landscapes remain active today. In places like Greenland and Antarctica, ice sheets continue the work of landscape sculpture, though at rates so slow they are barely measurable during human lifetime. The ice streams that drain these ice sheets are carving valleys beneath thousands of feet of ice, creating landscapes that will not be revealed until the ice retreats, if it ever does. The relationship between ice and stone creates landscapes of profound beauty and otherworldly geometry. Glacial polish can create rock surfaces so smooth they reflect light like dark mirrors. Glacial erratics, boulders transported far from their original locations, sit on landscapes where they clearly don't belong, like messages from distant mountains delivered by rivers of ice. These landscapes speak of forces so patient they can move continents, so persistent they can erase mountain ranges, so powerful they can redirect the flow of rivers and reshape the very foundations of the land we call home. And in their silence, these carved and sculpted spaces hold a question that echoes across deep time. What other familiar landscapes might be transformed if the ice returns? And what new forms of beauty might emerge from beneath the patient weight of frozen rivers, flowing once again across a cooling world? What waits below frozen ground? Seeds, bones, echoes of extinct creatures. We reflect on how fossilization under ice preserves both fragility and permanence, creating a museum of deep time where mammoth tusks emerge from thawing tundra like memories made manifest. And we wonder what other secrets lie sleeping in Earth's frozen vaults. The permafrost is Earth's deepest freezer, a layer of permanently frozen ground that in some places extends more than a mile beneath the surface. This frozen realm preserves organic matter, with a fidelity that defies time itself. While most fossils are formed through mineralization, soft tissues decomposing while hard parts are slowly replaced by stone, ice fossilization preserves the actual substance of ancient life. Skin, fur, muscle tissue, even DNA can survive in perfect suspension, waiting for the right moment to tell their stories. In Siberia, mammoth hunters search the banks of rivers where spring floods have eroded permafrost and revealed treasures from the Pleistocene. These are not professional paleontologists, but local people who have learned to read the landscape for signs of ancient elephant. A fragment of curved ivory protruding from a riverbank, a patch of brown fur emerging from ice, the mineral-stained earth that indicates decomposing organic matter. These are the clues that lead to discoveries that rewrite our understanding of extinct worlds. The preservation is so complete it can be startling. Mammoth carcasses emerge from the permafrost with their stomach contents intact, revealing not just what these animals looked like but what they ate, what diseases they carried, even what the climate was like during their final day. Scientists have found mammoth muscle tissue so well preserved that it still contains viable proteins after 40,000 years in the freezer of permafrost. But mammoths are just the beginning of this frozen bestiary. Woolly rhinoceros, cave lions, ancient horses, and giant bison all lie preserved in permafrost deposits across the Arctic. Each discovery is like opening a time capsule, revealing not just individual animals but entire ecosystems frozen in time. The permafrost preserves everything, from massive mammals to tiny insects, from pollen grains that reveal ancient vegetation to microscopic organisms that inhabited prehistoric soils.
Perhaps most remarkably, scientists have successfully germinated seeds from permafrost deposits that are over 30,000 years old. Saline stenophylla, a flowering plant native to Siberia, was resurrected from fruits found in an ancient ground squirrel burrow preserved in permafrost. The seeds not only germinated, but grew into healthy plants that produced flowers and fertile seeds of their own. These plants carried genes that had been absent from Earth's surface for millennia, genetic variations that had evolved in Ice Age climates and then lay dormant, waiting for their chance to breathe again. The preservation process in permafrost is elegantly simple yet remarkably effective. When organic matter freezes quickly and remains frozen, bacterial decomposition essentially stops. The cold temperatures slow molecular movement to a crawl, while the absence of liquid water prevents most chemical reactions that would normally break down organic compounds. The result is a form of preservation that maintains not just structure, but often function. DNA remains readable, proteins retain their shapes, even cellular structures can remain intact. This preservation extends beyond individual organisms to entire landscapes. Permafrost contains what scientists call yedoma, ancient loess deposits that accumulated during ice ages and contain perfectly preserved samples of entire ecosystems. These deposits can be dozens of feet thick and contain roots, leaves, pollen, insects and organic matter from Ice Age grasslands. When climate scientists want to understand what Ice Age ecosystems were like, they extract cores from yedoma deposits like reading pages from a 50,000-year-old book. The relationship between ice and fossilization creates preservation opportunities that exist nowhere else on Earth. Cave environments can preserve organic matter for thousands of years, but not tens of thousands. Tar pits can create excellent fossils, but they capture only animals unfortunate enough to become trapped. Permafrost, by contrast, preserves representative samples of entire ecosystems across vast geographic areas and immense spans of time. Some of the most remarkable permafrost discoveries challenge our understanding of deep time and extinction. In 2018, scientists discovered a perfectly preserved 18,000-year-old puppy in Siberian permafrost. The puppy's fur, teeth, and even eyelashes were intact, leading to questions about whether it represented a dog, a wolf, or something between the two, a genetic time capsule from the last ice age when the evolutionary relationship between dogs and wolves was still being written. The genetic material preserved in permafrost has opened new chapters in evolutionary biology. Ancient DNA extracted from permafrost specimens has revealed that woolly mammoths survived on Wrangel Island until just 4,000 years ago, well into the time of human civilization. The genetic diversity of these island populations, their adaptations to isolation, and the factors that led to their final extinction are all written in DNA preserved by permafrost. But permafrost preservation also raises profound questions about the nature of extinction and the boundaries between life and death. If genetic material can survive for thousands of years in frozen suspension, if seeds can remain viable for millennia, if entire ecosystems can be preserved intact, waiting for the right conditions to resume, then what do we mean when we say something is truly extinct? The thawing of permafrost due to warming temperatures creates both opportunities and urgency for paleontological discovery. As ancient ice melts, it exposes specimens that have been hidden for millennia, but it also threatens to destroy them through decomposition. Scientists race against time to document and collect specimens before they are lost forever, creating a window of discovery that may close as rapidly as it opens. Some permafrost fossils tell stories of catastrophic death, animals that died suddenly and were quickly buried by sediment or snow before decomposition could begin. Others suggest more gradual burial in environments where cold conditions slowed decomposition long enough for permafrost to form and preserve the remains. The distribution of specimens in permafrost deposits creates maps of ancient environments, showing where different species lived, what the vegetation was like, and how ecosystems changed as ice ages advanced and retreated. The preservation quality in permafrost sometimes approaches science fiction. Scientists have extracted liquid blood from a 42,000-year-old foal found in permafrost, blood so well preserved that individual red blood cells were still recognizable under microscopic examination. Hair and fur retain their original colors and textures, soft tissues maintain their flexibility and cellular structure. These specimens offer insights into ancient biology that would be impossible to obtain from traditional mineralized fossils. Viral and bacterial communities are also preserved in permafrost, creating libraries of ancient microbial life. Some of these microorganisms remain viable after thousands of years in frozen suspension, raising questions about the role of permafrost as a reservoir of ancient genetic material and a potential source of novel compounds for medicine and biotechnology. The preservation extends to traces of human activity as well. Arctic peoples have been hunting mammoths for thousands of years, and their tools, camps, and hunting sites are preserved in permafrost along with the remains of their prey. These sites provide unprecedented insights into how humans adapted to Ice Age environments and how they interacted with the megafauna that shared their world. As we consider the possibility of future ice ages, permafrost preservation suggests that our current biological world would not simply disappear but would be archived in frozen ground waiting for future discovery. The plants and animals living today, the ecosystems we consider normal, the genetic diversity that surrounds us, all of this could potentially be preserved in perfect detail for future paleontologists to discover and wonder at. And in this preservation, there is both comfort and melancholy. Comfort in knowing that life finds ways to persist across even the vastest gulfs of time, and melancholy in recognizing that perfect preservation often comes at the cost of life itself. But to be remembered forever, some things must first be willing to sleep in ice and wait for someone to listen to their frozen dreams. Civilization depends on stable seasons, gentle rains, and fertile soils. But what would unravel if warmth suddenly retreated? We imagine fields turning to tundra, rivers to ice, and harvests fading into hunger as the delicate systems that support 8 billion human lives begin to buckle under the patient pressure of returning cold. The mathematics of civilization are written in temperature. Every degree of warming or cooling cascades through systems we rarely consider: the timing of spring planting, the reliability of monsoons, the depth of winter frost, the length of growing season. Our entire agricultural system is calibrated to the climate patterns of the Holocene, the 11,700-year interglacial period that has provided the stable conditions within which human civilization developed. A return to Ice Age conditions would not simply be an inconvenience, it would represent a fundamental challenge to the assumptions upon which modern life is built.
Consider first the retreat of agriculture. The great grain belts of the world, the American Midwest, the Ukrainian steppes, the Chinese plains exist because these regions enjoy the precise combination of temperature, precipitation and soil conditions that allow crops to flourish. A cooling of just a few degrees would shorten growing seasons, reduce crop yields, and push the viable farming zone hundreds of miles toward the equator. The boreal forests that now ring the northern hemisphere would advance southward, reclaiming agricultural lands that have fed humanity for millennia. The timeline of agricultural collapse would not be uniform. Some regions would lose their viability within decades as changing precipitation patterns and shorter growing seasons made farming unreliable. Others might remain marginally productive for centuries, gradually declining as soils degraded and weather patterns shifted. The great river systems that have served as the arteries of civilization, the Nile, the Ganges, the Mississippi, would change their character as altered precipitation patterns and seasonal ice formation disrupted their flow. Water itself would become a different kind of resource. Currently, much of humanity depends on seasonal snowpack in mountains to provide river flow throughout the dry months. As Ice Age conditions advanced, more precipitation would fall as snow, but paradoxically less might be available for human use as vast quantities of water became locked in expanding ice sheets. The hydrological cycle would reorganize itself around the growing ice, creating new patterns of drought and abundance that would bear little resemblance to current water supplies. The energy demands of a cooling world would strain systems designed for our current climate. Heating requirements would increase dramatically in regions that currently require little winter heating. The infrastructure of energy distribution, power grids, natural gas pipelines, fuel supply chains would need to adapt to demands that could overwhelm current capacity. Coal and wood might regain importance as heating fuels, reversing centuries of transition toward cleaner energy sources. Transportation networks would face unprecedented challenges as weather patterns intensified and seasonal variations became more extreme. Shipping lanes might become impassable due to sea ice for larger portions of the year. Road and rail networks would require constant maintenance against freeze-thaw cycles that could become more severe. Aviation would need to adapt to changed jet stream patterns and more frequent severe weather events. The social fabric of civilization might prove even more fragile than its physical infrastructure. Mass migrations would become inevitable as entire regions lost their ability to support large populations. The movement of hundreds of millions of people seeking more hospitable climates would strain political systems and social institutions in ways we can barely imagine. Competition for arable land and water resources could trigger conflicts that would dwarf current resource wars. Urban areas would face particular vulnerability. Cities generate their own heat islands that moderate local climate, but they also concentrate populations that depend entirely on external resources for survival. The supply chains that keep cities fed extend across continents and depend on reliable transportation, predictable weather, and stable political conditions. Ice Age conditions would disrupt all of these systems simultaneously, creating cascading failures that could make many urban centers uninhabitable. The psychological impact of climatic collapse might prove as challenging as the physical effect. Human societies are remarkably adaptable, but they adapt best to gradual change that allows time for cultural and technological adjustment. Rapid climate shifts could overwhelm social learning systems, creating populations that lack the cultural knowledge to survive in their changing environment. The loss of place-based ecological knowledge as environments change faster than cultures can adapt would leave communities vulnerable in ways that go beyond mere material need. Yet within this collapse there would also be adaptation and innovation. Humanity has survived ice ages before, though in much smaller numbers and with simpler technologies. The ingenuity that has allowed our species to colonize every continent might find new expression in technologies and social systems designed for a cooling world. Underground cities, closed-loop agricultural systems, new forms of energy generation adapted to ice age conditions. The pressure of necessity might drive innovations we cannot currently imagine. Some regions might paradoxically benefit from ice age conditions. Areas currently too hot or dry for intensive agriculture might become more productive as weather patterns shifted. The reduced sea levels that accompany ice ages would expose vast areas of continental shelf that could provide new land for human settlement. The concentration of human populations into smaller habitable zones might drive technological innovation and social cooperation in ways that would be impossible under current conditions of global dispersal. The collapse would not be uniform or immediate. Different regions would experience different timelines of change, creating a patchwork of declining and adapting societies. Some areas might maintain industrial civilization for centuries after ice age conditions began, while others might revert to subsistence economies within decades. This uneven collapse would create new forms of inequality and interdependence as resource-rich regions became magnets for climate refuge. The institutional structures of modern civilization, governments, corporations, international organizations, are all calibrated to operate within current climatic conditions. A return to Ice Age conditions would challenge the basic assumptions of international law, economic systems and political boundaries. National borders drawn during the Holocene might become meaningless as the geography they were meant to encompass became uninhabitable or inaccessible. Perhaps most poignantly, the collapse of warmth would force humanity to confront the precariousness of our current prosperity. The abundance that supports modern civilization, cheap energy, global trade, industrial agriculture, urban concentration all depend on climatic conditions that are historically unusual and potentially temporary. A return to Ice Age conditions would strip away these supports and force humanity to rediscover more fundamental ways of living on Earth. The artifacts of our current civilization might themselves become fossils, preserved in advancing ice or buried under sediments for future discoverers to puzzle over. Our cities, our technologies, our accumulated knowledge might survive only as archaeological evidence of a brief moment when Earth's climate allowed a species of upright apes to build a global civilization during a temporary pause between ice ages. And in contemplating this we might find a strange kind of humility, recognizing that the warmth we consider normal is actually a gift of astronomical timing, and that the stability we assume will continue forever is actually a brief exception in Earth's longer story of ice and change, and the patient rearrangement of everything we think we know about what it means to be at home on this planet. As ice swallows water, oceans fall, exposing forgotten coastlines and ancient plains, and we walk through speculative memories of the world's drowned margins, resurfacing like ghosts returning from the deep, revealing landscapes that have been sleeping beneath the waves for thousands of years, waiting for the ocean's retreat to tell their stories. The ocean remembers every shoreline it has ever touched. Beneath the waves lie submerged river valleys, drowned forests and the remains of coastlines where early humans walked during the last ice age when sea levels were 400 feet lower than today. These underwater landscapes are not barren seafloor but complete terrestrial ecosystems, preserved in sediment and waiting for the ocean's retreat to expose them once again to air and light. During ice ages, so much water becomes locked in continental ice sheets that ocean levels drop dramatically, exposing vast areas of what we now call the continental shelf. The English Channel becomes dry land connecting Britain to Europe. A land bridge stretches from Siberia to Alaska, providing a pathway for both animals and humans to colonize new continents. The Persian Gulf vanishes entirely, revealing a river valley where the Tigris and Euphrates converge and flow toward a distant ocean. Indonesia and Australia merge into a single continent separated from Asia by narrow straits instead of deep ocean. This is not theoretical geography but documented fact. Marine archaeologists working with submersibles and underwater robots have mapped these drowned landscapes in extraordinary detail. They have found river channels carved into what is now seafloor, complete with meanders, oxbow lakes and tributary systems that match exactly what we would expect from terrestrial rivers. They have discovered the stumps of ancient forests, still rooted in place where they grew when the ocean was hundreds of feet lower. The Doggerland beneath the North Sea between Britain and Europe was once a vast plain crossed by rivers and populated by herds of mammoth, aurochs and deer. Archaeological evidence suggests it was also home to Mesolithic humans who lived along its rivers and coastlines, until rising seas finally submerged their world around 8th. Fishing nets occasionally pull up artifacts from this lost landscape: stone tools, carved antlers, even human remains, evidence of lives lived on land that now lies beneath hundreds of feet of seawater. But Doggerland is just one example of landscapes that emerge when oceans fall. The continental shelves of every ocean hide similar stories. Off the coast of Australia, Aboriginal oral traditions speak of times when people could walk to islands that are now separated by miles of open water, traditions that align perfectly with archaeological evidence of human occupation during periods of lower sea level. The precision of these cultural memories across thousands of years speaks to the profound impact of changing coastlines on human consciousness. The process of ocean retreat during Ice Age formation follows a predictable sequence. As snow accumulates in polar regions and fails to melt completely during summer months, it gradually compacts into glacial ice. This ice represents water that has been removed from the ocean and stored on land. Initially, the effect on sea level is minimal, a few inches or feet that go largely unnoticed. But as ice sheets grow to continental proportions, reaching thicknesses of miles in some places, the cumulative effect becomes dramatic. The relationship between ice volume and sea level follows simple physics. Every 350 feet of ice sheet thickness corresponds roughly to 1 foot of sea level drop. When ice sheets reach their maximum extent during glacial periods, covering much of northern North America and northern Europe with ice more than a mile thick, the cumulative water storage can lower global sea level by 400. This drop exposes approximately 10 million square miles of continental shelf, an area larger than North America. The exposed landscapes would not remain static. Rivers would quickly establish new courses to the lowered ocean, carving valleys across the newly exposed shelf. Vegetation would colonize the new land following predictable patterns of ecological succession. Animals would expand their ranges into the new territories, creating ecosystems that might persist for thousands of years, before rising seas reclaimed them. Some of these exposed lands would become crucial corridors for both animal and human migration. The Bering Land Bridge that connected Asia and North America during glacial periods was not a narrow isthmus, but a subcontinent hundreds of miles wide, rich in resources and supporting diverse ecosystems. Archaeological evidence suggests that humans lived on this exposed landscape for thousands of years, developing cultures adapted to its unique environment before rising seas eventually divided their world into separate continents. The rate of sea level change during ice age transitions can vary dramatically. Sometimes the ocean falls gradually over thousands of years, allowing ecosystems time to establish themselves on the newly exposed land. Other times, particularly during rapid ice sheet collapses, sea level can change by dozens of feet in a matter of centuries or even decades, creating catastrophic flooding that drowns vast areas almost instantaneously. These rapid changes are preserved in the geological record as catastrophic flood deposits and sudden shifts in marine sediment composition. They also survive in human cultural memory as flood myths that appear in cultures around the world. Stories of times when the sea suddenly rose and drowned familiar landscapes, forcing people to flee to higher ground or perish beneath the wave. The microbiology of newly exposed ocean floor would create unique ecological opportunities. Sediments that had been underwater for thousands of years would suddenly be exposed to air and colonized by terrestrial organisms. Salt-tolerant plants would be among the first colonizers, gradually giving way to less salt-tolerant species as rainfall leached salt from the exposed sediments. The succession from marine to terrestrial ecosystems might take centuries to complete. Fresh water would play a crucial role in transforming exposed ocean floor into habitable land. Rivers would establish new courses across the exposed shelf, carrying fresh water and sediment that would gradually create the soil conditions necessary for terrestrial plant growth. Springs and groundwater would create oases of fresh water in landscapes that might otherwise remain too salty for most terrestrial life. The archaeological potential of exposed continental shelf would be extraordinary. These areas preserve not just landscapes but also the artifacts and settlements of people who lived there during periods of lower sea level. Coastal settlements, which are often the most archaeologically rich sites on current land surfaces, would be found intact beneath current ocean waters, providing unprecedented insights into how human cultures adapted to changing coastlines. Some of the world's most important river systems would undergo dramatic changes as sea levels fell. The Amazon River during glacial periods would have extended its mouth hundreds of miles to the east, creating a vast delta system across what is now underwater. The Mississippi would have carved a deep canyon across the exposed Gulf of Mexico, creating landscapes reminiscent of the Grand Canyon but now hidden beneath the sea. The exposed lands would also create new weather patterns. Large continental areas that are currently underwater would generate their own climate systems, potentially creating rain shadows, seasonal temperature variations, and wind patterns that would influence regional climate far beyond the exposed areas themselves. Some climate models suggest that exposed continental shelves during glacial periods acted as massive continental areas that influenced global weather patterns. Marine life would need to adapt to the suddenly shrunken ocean base. Fish populations that currently migrate across continental shelves would find their habitats dramatically altered. Some species might become isolated in separate ocean basins, potentially leading to evolutionary divergence. Others might find new opportunities in the deeper, more concentrated ocean environment. The return of these landscapes would not be permanent. Ice ages end, ice sheets melt, and the ocean gradually reclaims the exposed land. But the memory of their existence would persist in multiple forms, in the cultural traditions of peoples who lived there, in the geological record of terrestrial sediments beneath marine deposits, in the genetic signatures of species that colonized and then were forced to retreat from the temporary lands, and in this cyclical exposure and drowning of vast landscape, we find perhaps the most dramatic example of Earth's capacity for transformation, the ability to create and destroy entire continents of habitable land, through the simple mechanism of storing and releasing water, reminding us that the maps we consider permanent are actually just snapshots of a moment in the planet's long conversation, between ice and ocean, land and sea, emergence and submersion in the endless dance of climate and coastline, that has shaped the story of life on Earth for millions of years. With colder air, clouds shift, winds wander, storms grow sharp, and we ask, would the sky look different? Would the blue above us grow brittle, as if silence itself had colored the atmosphere, transforming the very light that reaches our eyes, and changing the character of the air we breathe? The color of the sky is not constant across time. What we call sky blue is the result of very specific atmospheric conditions. The density of air molecules, the amount of water vapor, the concentration of aerosols and particles, the angle of incoming sunlight. Change any of these variables, and the sky transforms. An ice age atmosphere would create its own palette of colors, its own quality of light, its own relationship between Earth and space. In a colder world, the atmosphere itself becomes dense. Cold air holds less moisture than warm air, creating skies that are often clearer but also harsher. The reduced water vapor would mean fewer of the soft, high cirrus clouds that currently diffuse sunlight and create the gentle gradations of color we associate with dawn and dusk. Instead, the sky might take on a harder quality, more crystalline, more transparent, but also somehow more brittle, as if the cold had frozen the very air into something more glass-like than gas-like. The jet streams, those rivers of fast-moving air that circle the globe at high altitude, would reorganize themselves around the changed temperature gradients between pole and equator. Currently, these streams create relatively predictable weather patterns, but in an ice age climate with massive ice sheets covering much of the northern continents, the jet streams would follow different paths, creating new patterns of storms and calm, of clouds and clear sky. Dust would play a larger role in ice age atmospheres. The expanded areas of bare ground around the edges of ice sheets, the reduced vegetation cover, and the grinding action of glaciers would all contribute to increased atmospheric dust. This dust would create spectacular sunsets, perhaps more vivid than any we currently experience, as particles in the atmosphere scattered light in new ways. But it would also create a constant haze that might make the sky appear slightly milky or opalescent rather than the clear blue we consider normal. The aurora would dance across more southerly skies. The Earth's magnetic field interacts with charged particles from the solar wind to create the northern and southern lights, but the intensity and reach of these displays varies with solar activity and atmospheric conditions. In a colder world with different atmospheric chemistry and circulation patterns, the aurora might regularly be visible at latitudes where it currently appears only during the most intense magnetic storms. Imagine northern lights shimmering above ice-covered cities, creating natural illumination for long polar nights. Storm systems in an ice age atmosphere would have their own character. The temperature difference between the edge of continental ice sheets and the ice-free oceans would create powerful storm-generating zones. These storms might be more intense, but also more localized than current weather systems, creating a patchwork of violent weather and calm zones. The storms themselves might carry different kinds of precipitation, more snow, more ice, perhaps forms of frozen precipitation that don't commonly occur in our current climate. Cloud formation would follow new rules in a colder atmosphere. The reduced moisture-holding capacity of cold air would mean that clouds, when they did form, would be more likely to produce precipitation, rather than simply drifting across the sky. This could create a sky that alternates between stark clarity and intense precipitation events, with fewer of the gentle non-precipitating clouds that currently create much of the sky's visual texture. The optical properties of ice crystals in the atmosphere would create new types of halos, sundogs, and other atmospheric phenomena. Ice age skies might regularly display complex crystal formations that would create prisms and reflections in the air itself. The sky might shimmer with ice crystal displays that would make current atmospheric optics seem simple by comparison. Observers might regularly see multiple suns, lunar halos, and ice crystal formations that would turn the sky into a constantly changing display of natural optics. Visibility might improve dramatically in some ways while becoming more challenging in others. The clearer, drier air would allow distant objects to be seen with startling clarity, mountain ranges visible from hundreds of miles away, stars appearing brighter and more numerous than in our current atmosphere. But ice age atmospheres would also be subject to sudden changes in visibility as ice crystal fog, blowing snow, and dust storms created conditions that could reduce visibility to near zero in a matter of minutes.
The seasonal variation in sky appearance would become more extreme. Currently, most regions experience relatively gradual transitions between seasons in terms of sky appearance. In an Ice Age climate, the difference between summer and winter skies might be so dramatic that they would seem to belong to different planets. Summer might bring relatively familiar blue skies, while winter could transform the atmosphere into something almost alien in its clarity and color. Atmospheric pressure patterns would shift in ways that would create new relationships between weather and sky appearance. The massive weight of continental ice sheets would actually depress the land beneath them, potentially affecting local air pressure patterns. The cold air draining off ice sheets would create persistent high-pressure systems that might produce weeks or months of clear, cold weather, with skies so transparent they would seem almost empty. The interaction between atmospheric particles and sunlight would create new types of optical phenomena. Volcanic activity might increase due to the changing pressure on the Earth's crust as ice sheets grew and shrank, adding volcanic aerosols to the atmosphere that would create spectacular but ominous sunsets and unusual sky colors. The sky might regularly display colors that we currently see only after major volcanic eruptions: deep purples, unusual oranges, and copper-colored sunsets that would become the normal palette of Ice Age evening. Pilots navigating Ice Age skies would need to adapt to different atmospheric conditions. The jet streams would follow different paths, creating new patterns of turbulence and wind shear. The increased frequency of ice crystal formations in the atmosphere would create new types of aircraft icing conditions. Atmospheric electricity might behave differently, potentially creating more frequent or more intense lightning displays, or perhaps different types of electrical phenomena entirely. The psychological impact of changed skies should not be underestimated. Humans are deeply attuned to the subtle variations in light and sky that signal weather changes, seasonal transitions, and time of. An Ice Age atmosphere would require psychological as well as physical adaptation as people learn to read new types of cloud formations, new colors of light, new patterns of atmospheric behavior. Stargazing would be transformed by clearer, drier atmosphere. The reduced atmospheric moisture and potentially lower levels of atmospheric turbulence would create viewing conditions that might rival those currently found only at the world's best astronomical observatories. The night sky would appear deeper, darker, more filled with stars. The Milky Way might be visible as a brilliant river of light, even from populated areas, as the combination of clearer air and potentially less artificial lighting created optimal conditions for astronomical observation. Photography and art would need to adapt to the changed quality of light. The techniques developed for capturing and representing our current atmospheric conditions might prove inadequate for Ice Age skies. New aesthetic sensibilities would develop around the harsher, clearer light and the different color palettes that would characterize Ice Age atmosphere. And in this transformation of the sky itself, we might find one of the most intimate ways that climate change would affect human experience, changing not just the weather we endure or the landscapes we inhabit, but the very quality of light that reaches our eyes, the color of the dome above us, the character of the air through which we see our world, reminding us that even our most basic perceptual experiences are contingent on atmospheric conditions that we take for granted, but which exist only within a narrow range of Earth's possible climate, and that the blue sky we consider normal is actually a very specific gift of our current atmospheric moment. How would humanity resist the freeze? From ancient hearths to modern reactors, fire is our oldest ally, yet we wonder if even fire could hold back the encroaching glaciers of tomorrow, and what new forms of heat and light we might need to kindle if cold began its patient advance across a world grown suddenly hostile to warmth. Fire is the technology that made us human. The controlled use of combustion allowed our ancestors to extend their range into cold climates, cook foods that expanded their nutritional options, and create social spaces that fostered language and culture. In an Ice Age world, fire would once again become the thin line between survival and extinction, but the scale of the challenge would require fires beyond anything our ancestors could have imagined. The mathematics of heating a civilization are staggering. Currently, humanity consumes approximately 580 million terajoules of energy per year, much of it for heating, transportation, and industrial processes that would become even more energy-intensive in a colder world. The energy requirements for maintaining livable temperatures in Ice Age conditions could easily double or triple current consumption levels, and this at a time when many energy sources might become less reliable or less accessible. Wood, humanity's first fuel, would regain crucial importance in an Ice Age world, but the forests that currently provide biomass fuel would themselves be transformed by changing climate. Boreal forests might advance southward, potentially increasing wood availability in some regions, while cold-killed forests in others created vast stores of dead timber. The management of forest resources would become a matter of civilizational survival, requiring careful balance between harvesting for fuel and maintaining forest ecosystems for carbon storage and biodiversity. Coal would likely experience a renaissance despite current environmental concerns. The urgent need for concentrated, high-energy fuel sources might override climate considerations, especially if the world were already locked into Ice Age cooling. Coal deposits that are currently considered too environmentally costly to exploit might become essential resources for maintaining human civilization in a colder world. Underground coal fires might be deliberately maintained as permanent heat sources for community. Nuclear power would face both opportunities and challenges in an Ice Age scenario. The virtually limitless energy potential of nuclear fission and fusion would be attractive for large-scale heating applications, but the infrastructure requirements for nuclear power are enormous and would be challenging to maintain in a world of shifting populations and unstable political systems. Small modular reactors might become more appealing as community-scale heating sources that could provide reliable warmth without requiring massive electrical grid infrastructure. Geothermal energy would become increasingly valuable as surface temperatures drop. The contrast between cold surface conditions and the constant temperature of deep Earth would make geothermal systems more efficient and more appealing. Communities might reorganize themselves around geothermal resources, with hot springs and geothermal fields becoming the nuclei of human settlement in a cold world. The technology of heat distribution would need to evolve rapidly. Current heating systems are designed for relatively mild temperature differences between indoor and outdoor environments. Ice Age conditions might require new approaches to insulation, heat distribution, and building design. Underground communities might become common, taking advantage of the Earth's natural insulation and the ability to concentrate heat sources more efficiently. Solar power would face obvious challenges in a colder world, with potentially more cloud cover and shorter daylight hours in many regions. However, the high reflectivity of snow and ice might actually improve solar panel efficiency in some locations, and the extreme temperature differences between solar collectors and ambient air could improve the efficiency of some solar thermal systems. Biomass beyond traditional wood would become important. Agricultural waste, animal waste, and even human waste could become valuable fuel sources. Methane capture from landfills and waste treatment facilities might expand dramatically. The cultivation of high-energy crops specifically for fuel might compete with food production for limited arable land, creating difficult choices about resource allocation. Industrial waste heat would become a precious resource. Currently, enormous amounts of heat are generated as byproducts of industrial processes and simply released to the environment. In an Ice Age world, this waste heat would be captured and utilized for space heating, water heating, and other applications. Industrial processes might be redesigned with heat recovery as a primary consideration rather than an afterthought. Fire safety would take on new dimensions in a world where heat sources are essential for survival. The risk of losing heating systems to fire, equipment failure, or fuel shortage would become a life-or-death concern. Backup heating systems, fuel storage, and fire suppression technologies would all become critical infrastructure. Communities might maintain multiple redundant heating systems to ensure that no single failure could leave them without heat. The social organization around fire would echo ancient patterns while incorporating modern technology. Community heating systems might become more common than individual household heating, allowing for more efficient fuel use and backup systems. Fuel allocation and heat distribution could become matters of community governance, requiring new forms of social cooperation and resource sharing. Transportation fuels would need to be reconsidered for Ice Age conditions. Gasoline and diesel perform poorly in extreme cold, and the production and distribution infrastructure for petroleum products might be disrupted by changing weather patterns and shifting population. Alternative fuels that perform well in cold conditions might gain importance, even if they are less efficient or more expensive under current conditions. Energy storage would become crucial for surviving periods when fuel supplies are disrupted or energy generation is intermittent. Battery technologies would need to perform reliably in cold conditions. Thermal mass systems that store heat in stone,
water, or other materials might become important for maintaining warmth during periods when active heating systems are not operating. The efficiency of combustion would become a survival skill rather than just an environmental consideration. Clean burning technologies that extract maximum heat from limited fuel supplies would be essential. Traditional skills like banking fires, maintaining optimal combustion-air ratios, and fuel preparation might need to be relearned by populations that have lost these abilities in the age of automatic heating systems. Innovation driven by necessity might create new forms of fire and heat generation. Hydrogen fuel cells could provide clean, efficient heat without requiring traditional combustion. Advanced heat pump technologies might extract usable heat, even from very cold air. Concentrated solar power with thermal storage might provide heating even during cold, cloudy periods. The psychology of fire would regain its ancient importance. The hearth would once again become the center of human social life, not just as a source of physical warmth, but as a symbol of home, community, and safety. Fire-tending skills would become valued cultural knowledge passed between generations. The sound, smell, and sight of fire would provide psychological comfort beyond its physical warmth. Community fire management would require new forms of cooperation and governance. Fuel allocation, heat distribution, fire safety protocols, and backup systems would all require collective decision-making and resource sharing. Competition for fuel resources could create conflicts, while cooperation in fuel gathering and fire maintenance could strengthen community bonds. Large-scale heating projects might reshape human settlements. District heating systems powered by large central plants could serve entire communities from single efficient sources. Underground heat distribution networks could minimize heat loss while providing redundant pathways for heat delivery. Community-scale thermal mass systems could store heat during periods of abundant fuel and release it during shortages. Emergency heating systems would need to be robust and reliable. Portable heaters that could operate on multiple fuel types, emergency fuel supplies maintained in community stockpiles, and backup heating systems that could activate automatically if primary systems failed would all become essential infrastructure for Ice Age survival. And in humanity's relationship with fire in an Ice Age world, we might rediscover something fundamental about our species, that we are the creatures who learn to carry flame, to kindle warmth in cold places, to push back darkness and cold, with the controlled release of energy stored in carbon bonds, and that this ability to make fire might be the skill that allows us to survive not just individual cold nights, but the long, patient advance of ice across a world that has temporarily forgotten how to be warm. Ice ages bury species in silence, yet also give rise to new forms of life, and as we trace the record of extinctions we ask, who would vanish if tomorrow froze, and who might rise in the aftermath? Recognizing that every ice age creates both endings and beginnings in the long story of life on Earth. Extinction is not always dramatic, sometimes it arrives as quietly as snow, accumulating season by season until what once flourished can no longer find the conditions it needs to survive. The fossil record of ice ages tells us that climate change operates as one of evolution's most powerful editors, ruthlessly removing some species while creating opportunities for others, reshaping the cast of characters in Earth's biological drama with each advance and retreat of continental ice. The megafauna of the Pleistocene, giant ground sloths, saber-toothed cats, cave bears, Irish elk, and woolly mammoths, represent perhaps the most famous Ice Age extinction, but their disappearance was not sudden catastrophe but gradual attrition, as changing climates transformed the ecosystems that supported them. The vast grasslands that supported herds of mammoth and bison contracted as forests advanced during interglacial periods. The mixed woodlands that sheltered giant deer disappeared as ice sheets expanded during glacial periods. Each species that vanished was responding to environmental changes that unfolded over thousands of years. Yet the relationship between ice ages and extinction is more complex than simple climate determinism. Many of the large mammal extinctions that mark the end of the Pleistocene occurred not during the height of glacial periods, but during the transitions between ice ages and interglacials, when ecosystems were most unstable and changing most rapidly. It appears that many species could adapt to stable cold or stable warmth, but could not survive the transitional periods when everything was changing simultaneously. The pattern of Ice Age extinctions reveals important principles about which types of organisms are most vulnerable to climate change. Large animals with specialized diets and extensive habitat requirements tend to be more vulnerable than smaller, more generalist species. Animals that depend on stable ecosystems are more at risk than those adapted to disturbance and change. Species with slow reproduction rates and long generation times have more difficulty adapting to rapid environmental change than those with shorter life cycles and higher reproductive rates. Marine ecosystems during ice ages experienced their own patterns of extinction and evolution. As sea levels dropped and ocean temperatures changed, entire marine ecosystems were reorganized. Coral reefs retreated toward the equator, leaving behind fossil remnants in places where living coral cannot survive today. Cold water species expanded their ranges while warm water species contracted, creating entirely different marine communities from those we observe today. The plants tell their own story of ice age extinction and adaptation. Pollen preserved in sediments reveals that entire forest communities migrated hundreds or thousands of miles in response to changing climate. Some tree species that had grown together for millions of years were separated by ice age climate changes and never reunited. Other plant communities that we now consider natural assemblages actually formed only recently when ice age climate changes brought previously separated species together for the first time. But ice ages also created opportunities for evolutionary innovation. The fragmentation of habitats by advancing ice sheets created isolated populations that could evolve independently, leading to rapid speciation in some groups. The harsh conditions of ice age environments favored traits like cold tolerance, efficient metabolism, and behavioral flexibility that would prove advantageous in many different environments. Some of our most successful modern species groups, including our own, evolved during the climatically unstable conditions of the Pleistocene. Cave environments during ice ages served as refuges where species could survive harsh surface conditions, but they also created opportunities for evolutionary specialization. Cave fish lost their eyesight but developed enhanced senses of touch and chemical detection. Cave mammals developed unique metabolic adaptations to low oxygen environments. These cave-adapted species represent examples of evolution taking advantage of new niches created by ice age conditions. The relationship between human evolution and ice age extinctions remains one of paleontology's most debated topics. Did early humans contribute to megafauna extinctions through hunting pressure, or were climate changes the primary driver? The timing suggests a complex interaction between human activities and environmental change, with human hunting possibly providing the final pressure that pushed already stressed populations toward extinction. Island ecosystems provide particularly clear examples of ice age extinction patterns, because they create natural experiments in isolation and environmental change. As sea levels dropped during glacial periods, many islands became connected to mainlands, allowing new species to colonize while exposing island endemic species to new competition and predation. When sea levels rose again during interglacial periods, these newly mixed communities were isolated and forced to reorganize, often resulting in waves of extinction among species that could not compete in the new assemblage. The extinction patterns also reveal something profound about the relationship between biodiversity and stability. Ecosystems with higher diversity tend to be more stable and resilient to environmental change, while ecosystems with lower diversity are more vulnerable to collapse. Ice age climate changes repeatedly tested this relationship, and the fossil record shows that diverse ecosystems were more likely to maintain some version of themselves through climate transitions, while simpler ecosystems were more likely to be completely reorganized. Microorganisms, bacteria, viruses, fungi, and other microscopic life forms experienced their own patterns of ice age extinction and evolution, though these are much more difficult to detect in the fossil record. The changing chemistry of ice age oceans, the different soil conditions under ice sheets, and the altered atmospheric composition all created new selective pressures on microbial communities. Some modern disease organisms may have evolved during ice ages, as human and animal populations were concentrated into smaller ranges where infectious diseases could spread more easily. Pollinator networks were repeatedly disrupted and reformed during ice age cycles. As plant communities migrated and reorganized, the insects, birds, and mammals that pollinated them had to adapt to new relationships or face extinction. Some plant species that had evolved tight coevolutionary relationships with specific pollinators were separated by ice age climate changes and never reunited, forcing them to evolve new pollination strategies or face extinction. The speed of ice age environmental change appears to have been a crucial factor in determining extinction patterns. Species could often adapt to gradual climate changes over thousands of years, but rapid changes over decades or centuries overwhelmed adaptive capacity. This pattern has important implications for understanding how current rapid climate change might affect modern species. Genetic diversity within species was also shaped by Ice Age cycles. Species that survived Ice Ages often show patterns of genetic diversity that reflect their Ice Age history, reduced genetic diversity in populations that survived in small refugia, and mixed genetic signatures in populations that formed when previously separated groups came back together as climates changed. These genetic signatures are still detectable in modern species, and provide clues about how past climate changes shaped current biodiversity patterns. The recovery patterns after Ice Age extinctions reveal important principles about ecosystem resilience. Some ecosystems bounced back quickly when favorable conditions returned, while others remained simplified for thousands of years. The factors that determine recovery speed appear to include the availability of colonizing species from nearby refugia, the connectivity of habitats, and the stability of post-extinction environmental conditions. Looking toward future Ice Age scenarios, the current pattern of global species distributions suggests that a return to Ice Age conditions would likely cause extensive extinctions among species that are currently adapted to warm, stable climate. Tropical species with narrow temperature tolerances would be particularly vulnerable, while species already adapted to cold or variable conditions might expand their ranges. Human activities have already fragmented many habitats and reduced population sizes for many species, potentially making them more vulnerable to Ice Age extinctions than their ancestors were during previous glacial periods. And in this archive of vanishing and emerging life, we find one of evolution's most important lessons, that extinction and speciation are not opposite processes but complementary aspects of the same fundamental dynamic that has shaped life on Earth for billions of years, and that every Ice Age represents not just an ending but also a beginning, clearing ecological space for new evolutionary experiments and reminding us that in the long conversation between life and climate, both death and birth are necessary parts of the grammar that evolution uses to write the ever-changing story of what it means to be alive on a planet that never stops changing. If glaciers swept across cities, what traces of us would survive? Plastic, concrete, satellites, and steel might become technofossils, locked in crystalline memory waiting for distant eyes to rediscover, and we wonder what story our artifacts would tell about a species that briefly flourished during Earth's interglacial pause. The archaeological record of our civilization would be unlike anything preserved before in Earth's history. While previous mass extinctions left behind shells, bones, and the occasional imprint of soft tissues, we would bequeath a different kind of fossil assemblage, polymers that resist decay, concrete structures that might survive longer than mountains, and radioactive signatures that will persist for geological ages. Our technosphere, the sum total of human-made materials and structures, represents a new category of potential fossil that future paleontologists might struggle to understand. Consider the humble plastic bottle, now scattered in nearly every ecosystem on Earth. These polyethylene and PET containers, designed for convenience and disposability, possess a molecular stability that could preserve them for hundreds of thousands of years. Buried in advancing glacial sediments, frozen in permafrost, or compressed beneath accumulating ice, plastic objects would maintain their shape and chemical composition far longer than the organic materials that sustained the civilization that created them. Future discoverers might find intact plastic containers long after every wooden structure has decayed and every paper document has disintegrated. The urban landscape itself would create distinctive geological formation. New York City alone contains approximately 40 billion tons of concrete, steel, and other building materials, enough mass to create artificial mountain ranges if concentrated. As ice sheets advanced over cities, they would encounter resistance from skyscrapers and infrastructure unlike anything in their previous experience. Some structures might be ground down and incorporated into glacial till, creating unique geological deposits studded with steel rebar, glass fragments, and concrete chunks. Others might be buried intact, creating hollow spaces within glacial deposits that could preserve entire building interiors as time capsules. The electronic devices that define our current technological moment would create their own category of technofossils. Smartphones, laptops, and servers contain rare earth elements in concentrations far higher than their natural occurrence in Earth's crust. These concentrated deposits of exotic metals, neodymium, europium, terbium, would create geochemical anomalies detectable long after the devices themselves had been crushed beyond recognition. The silicon chips that store our information might survive as unusual crystal formations, their microscopic circuit patterns preserved like the cellular structures of ancient organisms. Nuclear materials would leave the most persistent signatures of our technological civilization. The radioactive isotopes produced by nuclear power plants, medical procedures and weapons testing have half-lives ranging from years to millions of years. Even if human civilization completely disappeared, the isotopic signatures of our nuclear age would remain detectable in ice cores, sediments and rock formations for geological time periods. Plutonium-39 with a half-life of 24,000 years would serve as a chronological marker for future geologists, attempting to date the Anthropocene layer in Earth's stratigraphic record. Satellites and space debris would create their own preservation challenges and opportunities. While most satellites would eventually decay and burn up in Earth's atmosphere, some might survive to impact the surface and become incorporated into glacial deposits. The materials used in space technology, titanium alloys, carbon fiber composites, specialized ceramics, are designed to survive extreme conditions and might persist as distinctive markers of our space age. The transportation infrastructure of our civilization would create linear features detectable even after burial beneath glacial deposits. Highways and rail lines represent massive earthworks that alter drainage patterns and create artificial ridges and valleys. The materials of this infrastructure, asphalt, concrete, steel rails, would weather at different rates, potentially creating distinctive topographic signatures that could persist for thousands of years, even after the original structures were no longer visible. Chemical pollution would leave its own fossil signature in the form of altered soil chemistry and unusual mineral formation. Heavy metals from industrial processes, pesticides from agricultural activities, and exotic chemicals from manufacturing would create geochemical environments unlike anything that occurred naturally before human industrial activity. Some polluted sites might develop unique mineral assemblages as contaminated groundwater interacted with natural geological processes over long time periods. The sheer volume of human-produced materials has already begun to alter Earth's surface geology in measurable ways. Concrete production alone has mobilized more material than all rivers combined transport to the oceans each year. This massive redistribution of materials, moving sand and gravel from quarries to cities, mining metals from deep deposits and concentrating them in surface structures, represents a geological force comparable to natural processes like volcanism or mountain building. Art and monuments designed to last might achieve their creators' intentions in unexpected ways. Mount Rushmore, carved from granite that has resisted millions of years of weathering, might survive glacial advance better than any other human creation. Bronze statues could persist for thousands of years, gradually developing patina layers that might be mistaken by future observers for natural mineral formation. The materials chosen for permanence, stone, bronze, ceramic, might outlast the more technologically sophisticated, but less durable materials of our electronic age.
Underground infrastructure would have the best chance of preservation. Subway tunnels, sewer systems, and utility networks might survive glacial advance as hollow spaces beneath the ice. These underground networks, with their distinctive geometries and material compositions, would create unique archaeological sites for future excavation. The rats, insects, and microorganisms that inhabit these underground spaces might also be preserved, creating an underground ecosystem frozen in time. The agricultural transformation of Earth's surface would leave subtle but extensive signatures. Field boundaries, drainage systems, and soil chemistry, altered by millennia of farming, would remain detectable long after farms were abandoned to advancing ice. The introduction of non-native species through agriculture and trade has created novel ecosystems whose fossil record would puzzle future paleontologists trying to understand how organisms from different continents came to be preserved together. Climate control systems and heating infrastructure would create distinctive archaeological deposits. The miles of ductwork, piping, and insulation that keep modern buildings habitable represent material investments comparable to ancient aqueducts or Roman roads. These systems, designed to move air and water efficiently, would create unique preservation environments for other artifacts if they were suddenly buried and sealed. The digital infrastructure that stores human knowledge would face particular preservation challenges. While the physical servers and data centers might survive burial for some time, the information they contain would likely be lost as power systems failed and storage media degraded. However, the electromagnetic signatures of our digital communications, radio, television, digital transmissions have already propagated beyond Earth at the speed of light and would provide evidence of our technological civilization to any observers capable of detecting them. even millions of years in the future. Garbage dumps and landfills would create stratified archaeological deposits that would provide detailed records of human material culture. These artificial geological formations, with their layered deposits of different types of waste materials, would offer future archaeologists unprecedented insights into the daily life of our civilization. The preservation conditions in landfills, anaerobic environments that prevent decay, might preserve organic materials that would disappear in other contexts. The isotopic signatures of our industrial activities would persist long after physical artifacts had vanished. Lead pollution from gasoline, uranium signatures from nuclear testing, and carbon isotope ratios altered by fossil fuel combustion would remain detectable in ice cores and sediment layers for hundreds of thousands of years. These chemical signatures might be among the most persistent evidence of our technological civilization. Medical and dental implants would create distinctive fossil assemblages, titanium joint replacements, stainless steel surgical hardware, and ceramic dental crowns represent materials and manufacturing techniques that have no natural analogues. Preserved in permafrost or glacial sediments, these artifacts would provide evidence not just of technological capability but of medical practices and perhaps even individual human anatomy. And in contemplating what traces of ourselves might survive an Ice Age burial, we confront both the permanence and the fragility of everything we have built, recognizing that our most durable creations might outlast our civilization by hundreds of thousands of years, while our most precious achievements in art, literature, and human knowledge might vanish without leaving any detectable trace, reminding us that the legacy we leave in stone and steel might be very different from the legacy we imagine we are creating in the minds and cultures of our descendants. Geology endures beyond the breath of ice, and as we imagine mountains wearing new scars, minerals reforming under frozen weight, and the slow whisper of entropy as stone outlasts memory, we discover that even the most permanent things we know are constantly changing, just on timescales that dwarf human perception. Mountains are not permanent. This truth requires a readjustment of human perspective so fundamental that it challenges our basic sense of what endures and what changes. The peaks that seem to define permanence itself, the Himalayas, the Rockies, the Alps, are actually engaged in constant motion, rising and falling, wearing away and reforming according to geological processes that operate with patience beyond human comprehension. An ice age would simply add another chapter to their long story of transformation. The weight of continental ice sheets during glacial periods can be so immense that it literally depresses the Earth's crust beneath it. The Greenland ice sheet, at its thickest points over a mile deep, has pushed the bedrock beneath it more than 1,000 feet below sea level. The Scandinavian peninsula, which was covered by ice sheets more than 2 miles thick during the last ice age, is still rising at a rate of nearly half an inch per year as the crust rebounds from the removal of that massive weight. This process, called post-glacial rebound, continues today, causing earthquakes in regions that seem geologically stable and gradually changing the relative levels of land and sea. But the relationship between ice and stone goes deeper than simple pressure and rebound. Glacial ice, loaded with rock debris and moving under tremendous pressure, acts as a geological force capable of carving, polishing, and reshaping bedrock on a massive scale. The Canadian Shield, the ancient geological core of North America, bears the scars of multiple ice ages in the form of countless lakes, smooth bedrock surfaces, and distinctive grooves that reveal the direction of ice flow from glacial periods millions of years ago. The grinding action of glaciers creates rock flour, finely pulverized stone, that gives glacial rivers their distinctive milky appearance. This process represents the literal consumption of mountains, the slow but inexorable reduction of stone to sediment that will eventually be carried to distant oceans and perhaps someday rise again as new mountains in Earth's endless cycle of geological renewal. A single large glacier can produce thousands of tons of rock flour each day, quantifying the rate at which moving ice consumes solid stone. Chemical weathering under ice sheets creates unique mineral environments. The chemistry of water changes under pressure and in the absence of oxygen. Minerals that are stable at surface conditions can become unstable under ice sheets, while new minerals can form that would be impossible to create under normal surface conditions. The rocks beneath ice sheets undergo chemical changes that can alter their composition, structure, and even their color, creating mineralogical signatures that persist long after the ice has melted. Permafrost creates its own unique geological environment where the normal processes of chemical weathering are slowed or stopped entirely. Rock formations that would normally weather away over thousands of years can remain unchanged for hundreds of thousands of years when frozen solid.
This preservation can create landscapes where ancient geological processes remain visible with startling clarity, like natural museums where the Earth's history is displayed in perfect preservation. The thermal effects of ice sheets on underlying bedrock create complex patterns of heating and cooling that can affect rock stability. While the surface of the ice sheet may be far below freezing, the base of a thick ice sheet can be at or above the melting point due to pressure and geothermal heat from below. This creates a unique environment where liquid water exists beneath ice at temperatures that would normally freeze it solid, leading to complex interactions between ice, water, and rock that can alter the chemical and physical properties of bedrock. Volcanic activity can be affected by the loading and unloading of ice sheets. The pressure of massive ice sheets can suppress volcanic activity by pressing down on magma chambers, while the rapid removal of ice can trigger increased volcanic activity as pressure is released. Iceland, which sits on a volcanically active ridge, experiences more volcanic activity during periods of glacial retreat, suggesting that the melting of ice sheets can literally influence the behavior of molten rock deep beneath the surface. The sedimentary record created by ice sheets provides some of the most detailed records of Earth's geological history. Glacial deposits preserve information about not just the ice sheets themselves, but about the climate, geography, and even the atmospheric composition of ancient periods. Vast seasonal layers in glacial lake deposits can provide year-by-year records of environmental conditions, creating geological calendars that rival tree rings in their precision and detail. Glacial erosion can expose rocks that formed deep within the Earth's crust, bringing to the surface minerals and rock types that would normally remain hidden miles below ground. The exposure of these deep crustal rocks can reveal the ancient history of continents, showing how they formed, moved, and collided over billions of years. Some of the oldest rocks on Earth are exposed in areas that were heavily glaciated, suggesting that ice erosion played a role in revealing Earth's most ancient geological secrets. The relationship between stone and ice operates on multiple timescales simultaneously. Over thousands of years, glaciers carve valleys and reshape landscapes. Over millions of years, the advance and retreat of ice sheets creates cycles of erosion and deposition that build up sedimentary sequences thousands of feet thick. Over hundreds of millions of years, the movement of continents into and out of polar positions drives ice age cycles that can influence the formation and destruction of entire mountain ranges. Tectonic activity can be influenced by ice sheet dynamics in ways that connect the fastest and slowest geological processes. The rapid melting of ice sheets can trigger earthquakes as crustal stresses adjust to changing load. The weight of ice sheets can influence the flow of molten rock in the Earth's mantle, potentially affecting the movement of tectonic plates themselves. These connections suggest that ice ages are not just surface phenomena but events that can influence geological processes throughout the Earth's system. Mineral formation under glacial conditions can create unique geological deposits. Some types of ore deposits appear to be associated with glacial processes, either through the concentration of minerals in glacial sediments, or through chemical processes that occur in the unique environments beneath ice sheets. The economic geology of formerly glaciated regions often reflects the influence of ice on mineral distribution and concentration. Karst landscapes, regions where water has dissolved limestone and other soluble rocks to create caves, sinkholes, and underground drainage systems, can be preserved or modified by glaciation in complex ways. Ice can fill cave systems, preserving them from further dissolution while also potentially crushing or deforming them under pressure. The interaction between glacial processes and karst geology creates some of the most unusual and spectacular landscapes on Earth. The preservation of ancient surfaces under ice sheets can create geological time capsules where features that would normally be erased by millions of years of weathering remain intact. Some surfaces beneath the Antarctic ice sheet appear to preserve features that formed before the ice sheet existed, creating windows into ancient geological periods that would be impossible to study anywhere else on Earth. Metamorphic processes. The transformation of rocks under heat and pressure can be influenced by glacial loading in subtle but important ways. The pressure of ice sheets can contribute to metamorphic processes, while the thermal effects of ice sheets can create unique temperature and pressure conditions that produce distinctive metamorphic mineral assemblages. The fracturing and jointing of bedrock under glacial stress creates patterns of weakness that influence how rocks respond to weathering and erosion long after the ice has disappeared. Glacially influenced joint patterns can control the development of valleys, the location of waterfalls, and the stability of rock slopes for millions of years after glaciation has ended. And in this long patience of stone beneath ice, we find perhaps the most humbling perspective on geological time. the recognition that processes we consider permanent operate on timescales so vast they make human civilization appear as brief as a lighting flash. Yet these same processes created the landscapes we call home, and will continue shaping the Earth long after our species has either evolved into something unrecognizable or joined the vast majority of species that have existed in the fossil record of extinction. Reminding us that stone itself is not permanent but simply changes more slowly than we can perceive, teaching us patience with the deep rhythms of planetary change. Is Earth itself alive in cycles of heat and silence? We consider speculative theories of planetary memory, entropy, and whether ice is not punishment but simply the way Earth dreams in longer seasons, breathing in rhythms so vast they encompass the rise and fall of species, the drift of continents, and the slow pulse of magnetic reversal. The Gaia hypothesis suggests that Earth functions as a single self-regulating organism, maintaining conditions suitable for life through complex feedback loops between the atmosphere, oceans, land surface, and living organisms. From this perspective, ice ages are not random climatic accidents but part of Earth's regulatory system, planetary fever and chills that maintain long-term stability by preventing the system from settling into states that might ultimately prove unstable or unsuitable for life. Consider the relationship between ice ages and atmospheric carbon. During glacial periods, atmospheric carbon dioxide levels drop dramatically as cold oceans absorb more CO2 from the atmosphere, and reduced plant respiration locks carbon in frozen organic matter. During interglacial periods, warming releases this stored carbon back to the atmosphere. This cycle suggests a planetary thermostat that operates over thousands of years, preventing Earth from either freezing permanently or warming to levels that might threaten the survival of complex life. The magnetic field of Earth provides another lens through which to consider planetary consciousness. Magnetic reversals, periods when Earth's magnetic north and south poles switch positions, occur on timescales similar to climate cycles, though not in perfect synchrony. These reversals affect the protection Earth provides against cosmic radiation, and may influence atmospheric chemistry and climate. Some researchers speculate about connections between magnetic field behavior and ice age cycles, suggesting that both might reflect deeper rhythms in Earth's core dynamics. Plate tectonics operates on timescales that encompass multiple ice age cycles, suggesting another level of planetary rhythm. The movement of continents affects ocean circulation patterns, atmospheric composition, and the distribution of land masses relative to polar regions. The current configuration of continents, with Antarctica positioned over the South Pole and the Arctic Ocean surrounded by land masses, creates conditions that favor ice age cycle. This continental arrangement has persisted for millions of years, suggesting that Earth's current ice age epoch might reflect a temporary phase in plate tectonic evolution. Volcanic activity pulses in patterns that some researchers associate with long-term climate cycle. Periods of increased volcanism can affect global climate through the injection of aerosols into the atmosphere, while periods of reduced volcanism might allow other climate drivers to become more dominant. The relationship between volcanism and ice ages remains controversial, but some evidence suggests that both phenomena might reflect deeper cycles in Earth's internal heat engine. The biosphere itself participates in these planetary rhythms in ways that blur the boundary between living and non-living systems. The evolution of photosynthesis fundamentally altered Earth's atmosphere, creating conditions that made ice ages possible. The evolution of complex life forms, from shell-building organisms to forest ecosystems, continues to influence atmospheric composition and climate regulation. From this perspective, ice ages might represent periods when the biosphere reorganizes itself, testing new evolutionary strategies and eliminating approaches that prove unworkable. Ocean circulation patterns provide perhaps the clearest example of planetary-scale regulatory mechanism. The thermohaline circulation, the global conveyor belt of deep ocean currents driven by differences in temperature and salinity, redistributes heat around the planet and plays a crucial role in climate regulation. This circulation system can exist in multiple stable states, and transitions between states might trigger rapid climate changes that appear sudden compared to the gradual orbital forcing of ice age cycle. The concept of planetary memory suggests that Earth retains information about past climate states in ways that influence future behavior. Ice cores preserve atmospheric composition from hundreds of thousands of years ago, Sedimentary rocks record climate conditions from millions of years ago. Even the isotopic composition of ocean water carries signatures of ancient ice volumes. This preservation of information might allow Earth's climate system to remember previous states and return to them under appropriate triggering conditions. Entropy and information theory provide another framework for understanding ice age cycles. Climate systems exist far from thermodynamic equilibrium, maintaining their organization through constant energy flows from the sun. Ice ages might represent periods when the climate system reorganizes itself to dissipate energy more efficiently, creating temporary states of higher organization that eventually give way to different organizational patterns as boundary conditions change. The relationship between Earth's orbital cycles and ice ages suggests a form of planetary resonance with astronomical forces. The Milankovitch cycles provide external pacing for ice age rhythms, but Earth's climate system responds to this pacing in ways that amplify small orbital changes into dramatic climate shift. This amplification suggests that Earth's climate system is poised near critical thresholds where small changes can trigger large responses, a characteristic of complex adaptive systems. Some researchers have proposed that ice ages serve a planetary function in maintaining genetic diversity by fragmenting habitats and creating evolutionary pressure that drives speciation. From this perspective, ice ages might be Earth's way of experimenting with different forms of life, testing survival strategies and maintaining the genetic variety necessary for long-term evolutionary resilience. The rapid speciation that occurs during climatically unstable periods supports this interpretation. The cycling of elements through Earth systems, carbon, nitrogen, phosphorus, sulfur, operates on multiple timescales that interact with ice age cycles in complex ways. Ice ages affect weathering rates, ocean chemistry, atmospheric composition and biological productivity in ways that alter the cycling of these essential elements. These changes might serve regulatory functions that maintain elemental balance over geological timescale. Consciousness and awareness at planetary scales remain speculative concepts, but some researchers explore whether complex systems like Earth's climate might exhibit emergent properties analogous to consciousness. The ability of climate systems to maintain homeostasis, respond to perturbations, and exhibit memory-like behavior suggests information processing capabilities that might represent a form of planetary cognition, even if very different from biological consciousness. The relationship between ice ages and human evolution raises questions about whether planetary climate cycles might serve as evolutionary forcing functions that drive the development of intelligence and consciousness. The climatic instability of the Pleistocene appears to have accelerated human evolution, selecting for cognitive flexibility and cultural adaptation that eventually led to civilization. This pattern suggests that planetary climate variability might play a role in the emergence of consciousness within the biosphere. Solar system dynamics provide context for Earth's climate cycles that extends beyond our planet. Other planets have experienced their own climate changes over geological time. Mars appears to have lost its atmosphere and water while Venus developed a runaway greenhouse effect. Earth's ability to maintain liquid water and a habitable atmosphere for billions of years might reflect regulatory mechanisms that operate as part of a larger solar system evolution. The anthropic principle, the observation that Earth's properties appear fine-tuned for the existence of life, raises questions about whether ice age cycles serve functions in maintaining this habitability. The cycling between glacial and interglacial conditions might prevent Earth from settling into permanent states that would be less suitable for life, maintaining the dynamic stability necessary for continued biological evolution. Deep time perspectives on ice ages reveal patterns that suggest cyclical behavior on multiple scales. The current ice age epoch, which began about 2.6 million years ago, is itself embedded within longer climate cycles that extend tens of millions of years into the past. These longer cycles might reflect even deeper planetary rhythms related to processes in Earth's core, mantle dynamics or astronomical cycles beyond the Milankovitch periods. And in considering whether Earth dreams in seasons of ice and warmth, we encounter one of the most profound questions about the nature of planetary systems: whether the complex self-regulating behavior of Earth's climate represents a form of planetary intelligence operating on timescales so vast that individual species, ecosystems, and even geological epochs become like thoughts in a mind that thinks in millions of years, dreams in ice ages, and awakens in periods of warmth and biological abundance, reminding us that our human perspective on planetary change might be as limited as a microorganism's perspective on the behavior of the organism it inhabits. We look inward if landscapes freeze, do our inner worlds freeze too? Identity, memory and perception blur as we ask whether the human mind is shaped, like stone, by the climate it inhabits, and whether consciousness itself might carry within it the same cycles of warmth and cold that drive the planet's long dream. The relationship between external climate and internal psychological states runs deeper than metaphor. Seasonal affective disorder demonstrates that human consciousness responds directly to changes in light and temperature, but this represents only the most obvious manifestation of connections that may extend far into our evolutionary and psychological development. If ice ages shape the evolution of species, they must also shape the evolution of consciousness, memory and the fundamental ways we perceive and organize reality. Human neural development requires specific temperature range. The brain generates its own heat through metabolic activity, but extreme cold affects neural transmission, memory formation and cognitive process. In ice age conditions, the energy cost of maintaining brain temperature would increase dramatically, potentially affecting not just individual cognitive function, but the evolutionary pressure on brain size, structure, and efficiency. The relationship between climate and cognition operates at both immediate and evolutionary timescales. Memory itself might be shaped by climatic conditions in ways we barely understand. The hippocampus, crucial for memory formation, contains neurons that are sensitive to temperature change. Chronic cold stress affects memory consolidation and retrieval. If human populations experience thousands of years of ice age conditions, these effects might accumulate into changes in how memory functions, how information is stored and accessed, and perhaps even how consciousness organizes itself around the storage and recall of experience. The psychological concept of seasonal thinking suggests that human cognitive processes naturally align with environmental cycles. During winter months, many people report changes in creativity, problem-solving approaches, and emotional process. If ice age conditions extended winter-like psychology across multiple generations, human consciousness might develop fundamentally different characteristics, perhaps more focused on survival and immediate problem-solving, less inclined toward abstract thinking and long-term planning. Language itself bears traces of climatic influence. Populations that have lived in cold climates for thousands of years often develop vocabularies with extensive terminology for different types of snow, ice and cold conditions. These linguistic adaptations represent more than practical necessity. They reflect different ways of perceiving and categorizing experience. An ice age civilization might develop forms of language and thought that are as different from current human consciousness as our consciousness is from that of tropical hunter-gatherers. The relationship between landscape and psyche operates through multiple channels. Environmental psychology demonstrates that physical surroundings affect mood, creativity and cognitive performance. The vast simplified landscapes of ice age conditions, endless snowfields, reduced biodiversity, stark seasonal contrasts, would provide very different psychological inputs than the complex, varied environments most humans currently inhabit. The human mind, shaped by millions of years of evolution in varied landscapes, might require fundamental adaptation to maintain psychological health in ice age conditions. Cultural memory operates on timescales that bridge individual psychology and collective consciousness. Oral traditions preserve information across generations, but they also shape how populations understand their relationship to environmental change. Communities that have lived through rapid climate changes often develop cultural practices, stories and psychological strategies that prepare subsequent generations for environmental uncertainty. Ice age populations might develop forms of cultural memory specifically adapted to cyclical environmental change. The concept of ecological unconscious suggests that human psychological health depends on our relationship with natural systems. As ice ages simplify ecosystems and reduce biodiversity, this ecological unconscious might experience a form of impoverishment that affects mental health, creativity, and spiritual well-being. The psychological effects of environmental simplification might be as significant as the physical challenges of surviving in colder conditions. Circadian rhythms, which regulate sleep, mood, and cognitive function, are closely tied to patterns of light and dark. Ice age conditions would dramatically alter these patterns, with long periods of darkness in winter and extreme seasonal variations in daylight. Human psychology would need to adapt to these altered rhythms, potentially developing different sleep patterns, different cycles of activity and rest, and different relationships between consciousness and unconscious.
The stress physiology associated with chronic cold exposure affects neurotransmitter production, hormone levels, and brain chemistry. Populations living under Ice Age conditions for extended periods might develop different baseline psychological states, perhaps more focused on immediate survival, more sensitive to environmental threats, less prone to the kind of relaxed exploratory consciousness that characterizes much human experience in temperate conditions. Collective psychology might shift toward different values and priorities under Ice Age conditions. The psychological traits that support survival in harsh conditions, caution, conservatism, focus on immediate needs, might become more prominent in population-wide psychological profiles. The optimism and future orientation that characterize much human planning might give way to more conservative, present-focused psychological strategies adapted to uncertain and threatening conditions. The relationship between individual and group consciousness might also change under Ice Age conditions. Survival in harsh climates often requires tight social cooperation, shared decision-making, and subordination of individual preferences to group needs. The individualistic consciousness that characterizes much modern human psychology might prove maladaptive under Ice Age conditions, leading to evolution toward more collectively oriented forms of consciousness. Creativity and innovation might follow different patterns under Ice Age psychological conditions. While harsh conditions often drive technological innovation, they might simultaneously constrain other forms of creative expression. The elaborate artistic traditions, complex musical forms, and abstract philosophical systems that flourish in stable, prosperous conditions might give way to more utilitarian forms of cultural expression, focused on survival skills and environmental adaptation. The development of children's consciousness would be particularly affected by Ice Age conditions. Early childhood development is highly sensitive to environmental conditions, stress levels, and social dynamics. Children growing up under Ice Age conditions might develop different cognitive abilities, different emotional regulation strategies, and different relationships to risk, uncertainty, and environmental change than children growing up in stable temperate conditions. Religious and spiritual consciousness might also adapt to Ice Age conditions in distinctive ways. Many spiritual traditions emphasize humanity's relationship with natural forces, seasonal cycles, and environmental change. Ice Age spirituality might develop particularly intense relationships with concepts of scarcity, survival, death, and the power of natural forces. The forms of consciousness that we associate with spiritual experience might be shaped by the environmental conditions within which they develop. The phenomenology of Ice Age consciousness, the actual subjective experience of being aware under such conditions, might differ fundamentally from current human experience. The constant awareness of environmental threat, the simplified sensory environment, the altered social dynamics, and the changed relationship with time and seasons might create forms of conscious experience that would be difficult for us to imagine from our current perspective. Psychological resilience mechanisms would need to evolve to help human consciousness maintain stability under Ice Age conditions. The cognitive strategies, emotional regulation techniques, and social support systems that currently help humans cope with adversity might prove insufficient for the sustained challenges of Ice Age survival. New forms of psychological resilience might need to emerge through both cultural innovation and possibly evolutionary change. The relationship between consciousness and landscape operates through multiple sensory channels. The reduced visual complexity of Ice Age environments, the altered acoustic environment, the different tactile experiences associated with cold conditions, and the changed chemical environment that affects smell and taste, would all contribute to different forms of sensory consciousness. Human awareness itself might become differently organized around these altered sensory inputs. Time perception might also change under Ice Age conditions. The long dark winters and extreme seasonal variations might affect how consciousness experiences duration, sequence, and temporal relationship. The psychological present might expand or contract in response to environmental conditions that make long-term planning more difficult and immediate survival more pressing. And in these mirrors of the mind reflecting climatic change, we discover perhaps the most intimate way that Ice Ages would transform human experience, not just changing the external conditions within which we live, but potentially altering the very nature of consciousness itself, reshaping memory, perception, creativity, and awareness in ways that would make Ice Age humans as psychologically distinct from us as we are from our Paleolithic ancestors, reminding us that the mind itself is not separate from the environment, but is part of the same planetary system that breathes in Ice Ages and exhales in interglacial, suggesting that consciousness and climate may be more deeply intertwined than we have ever imagined. If another Ice Age began tomorrow, What fragments of us would remain in the distant future? Dust, echoes, silence, and perhaps a trace of wisdom hidden under the ice, waiting for someone to listen. We close with reflections on legacy, memory, and the deep humility of recognizing our place in Earth's longer story of change. The question is not whether we will leave traces, but what kind of traces we will leave and who might eventually discover them. Every civilization that has ever existed has imagined itself permanent, yet we live surrounded by the fragments of forgotten worlds. The ancient Mesopotamians who invented writing believed they were recording eternal truths. The Romans who built roads across continents expected their empire to last forever. The medieval builders of cathedrals planned for eternity. Yet here we are, reading their artifacts like messages from alien worlds. And someday our own artifacts will be similarly mysterious to eyes we cannot imagine. The stratigraphic record that would preserve evidence of our civilization would be unlike anything in Earth's previous history. The Anthropocene layer, the geological signature of human activity, would appear in future rock formations as a thin but distinctive band marking a brief period when one species temporarily dominated planetary system. This layer would contain isotopic signatures from nuclear testing, microplastics distributed globally through ocean and atmospheric circulation, and geochemical anomalies from industrial activity. Future geologists would recognize this layer as marking a period of rapid environmental change, even if they could not initially interpret its causes. Our cities would leave different types of traces depending on their location and construction. Coastal cities, already threatened by sea level rise, might be quickly submerged and buried in marine sediments, preserving their basic outlines like underwater Pompeius. Inland cities might be gradually dismantled by advancing glaciers, their materials scattered across thousands of square miles as glacial erratics, steel beams and concrete blocks transported far from their origins, and deposited in alien landscapes where future discoverers would puzzle over their presence. The infrastructure of global communication would leave perhaps the most extensive but ephemeral traces of our civilization. The cables that carry internet traffic across ocean floors, the towers that relay cellular signals, the satellites that orbit Earth, these networks represent humanity's attempt to connect every part of the planet into a single communication system. But they are also among our most fragile technologies, dependent on constant maintenance and vulnerable to environmental change. Future archaeologists might find fragments of fiber optic cables and wonder about the civilization that needed to transmit information at the speed of light. Language itself would face extinction along with the speakers who maintain it. The thousands of human languages currently spoken represent an irreplaceable library of different ways of understanding and describing the world. Each language encodes unique knowledge about local environments, cultural practices, and ways of thinking. An ice age that forced massive population movements and cultural disruption would inevitably lead to language loss on a scale that would impoverish human consciousness even among the survivors. The digital legacy of our civilization presents unique preservation challenges. We have created more information than any previous civilization, but we have stored most of it in formats that are extraordinarily fragile and dependent on complex technological infrastructure. The books written on paper might outlast the digital libraries stored on magnetic media. The stone tablets created by ancient civilizations have proven more durable than the cloud servers that store our contemporary knowledge. Genetic traces of our domesticated species would persist long after human civilization had adapted or disappeared. Corn, wheat, and rice are so genetically modified by human selection that they could not survive without human cultivation, but their genetic signatures would remain in any preserved seeds or plant material. Domestic animals might survive as feral populations, but they would carry genetic markers of human selection that would be detectable for thousands of years. The artistic achievements that we consider our greatest cultural legacy, music, literature, visual arts, would face the most precarious survival prospects. These achievements depend not just on physical preservation, but on the cultural knowledge necessary to interpret and appreciate. A future civilization discovering a Bach score or a Beethoven symphony would need to reconstruct not just the notation system, but the entire cultural context within which these works acquired meaning. Nuclear waste would provide perhaps the most persistent signature of our technological civilization. The radioactive materials we have created will remain hazardous for periods ranging from thousands to millions of years. Future civilizations encountering these materials would need to develop sophisticated technologies just to detect and understand their danger. The markers we have designed to warn future peoples about nuclear waste sites represent our attempt to communicate across time spans longer than recorded history,
Scientific knowledge, ironically, might prove both our most valuable and most vulnerable legacy. The understanding we have developed about natural systems, mathematical relationships and physical laws represents genuine discoveries about the nature of reality. But this knowledge exists primarily in the minds of living scientists and in recorded forms that depend on technological infrastructure for preservation and transmission. The agricultural transformation of Earth's surface would remain detectable for thousands of years. Soil chemistry altered by industrial fertilizers, the genetic signatures of crop plants and the landscape modifications created by large-scale farming would all provide evidence of human agricultural activity. Future ecologists would be able to detect the period when humans replaced natural ecosystems with simplified agricultural systems across vast areas of the planet's surface. Climate data might provide the clearest record of human influence on planetary systems. The atmospheric changes we have caused increased greenhouse gas concentrations, altered isotopic ratios, novel chemical compounds would remain detectable in ice cores and sediment records for hundreds of thousands of years. Future climate scientists would be able to identify the period when atmospheric composition changed rapidly due to human activities, even if they initially misinterpreted the causes. Medical knowledge and practices might leave subtle traces in the human remains that survive from our period. Dental work, surgical implants, and the signatures of medical treatments would provide evidence of sophisticated healthcare system. The genetic consequences of medical interventions, increased survival of individuals with genetic conditions, altered disease resistance patterns, might remain detectable in future human populations. The philosophical and ethical frameworks we have developed for understanding human relationships, environmental responsibility and social organization represent perhaps our most important intellectual achievement. But these abstract concepts depend entirely on cultural transmission. For their survival, the values we consider fundamental: human rights, environmental protection, democratic governance, would need to be rediscovered and justified anew by future civilization. Space exploration provides our most likely path to creating permanent records that could survive planetary catastrophe. The messages we have sent into space, the artifacts we have placed on other planets, and the radio signals that have already propagated beyond our solar system represent humanity's attempt to communicate with unknown intelligences across vast distances and time periods. These space-based records might outlast any traces of human civilization on Earth itself. The deep geological repositories we have created for nuclear waste storage represent unintentional time capsules that could preserve detailed information about human technology and society. These repositories are designed to remain stable for hundreds of thousands of years, potentially making them among the most durable archives of human civilization. Future archaeologists discovering these sites might find them to be among the richest sources of information about human technology and social organization. Indigenous knowledge systems that have persisted for thousands of years might prove more resilient to environmental change than our technological civilization. Oral traditions, ecological knowledge, and cultural practices that have already survived multiple environmental changes might continue to carry information about sustainable relationships with natural systems long after other forms of human knowledge have been lost. The emotional and spiritual dimensions of human experience, our capacity for love, creativity, wonder, and transcendence would survive only if they could be recreated by future consciousness. These aspects of humanity cannot be preserved in any physical form but must be lived and experienced anew by each generation. The loss of the cultural contexts that nurture these capacities might represent the most profound diminishment of human potential in a post-Ice Age world. Perhaps the most important legacy we could leave would be the example of a species that recognized its impact on planetary systems and attempted to develop sustainable relationships with the natural world. The environmental movement, renewable energy technologies, and conservation efforts represent humanity's growing recognition of its responsibility as a planetary force. These efforts, even if they prove insufficient to prevent major environmental changes, might provide valuable lessons for future civilizations facing similar challenges. And in contemplating what would remain of our brief moment of planetary influence, we are led to a profound recognition of both the grandeur and the fragility of everything we have built and discovered and dreamed, understanding that our greatest achievements may prove as temporary as morning frost, while our most persistent traces may be the unintended consequences of industrial activities we barely considered, reminding us that legacy is not what we plan to leave behind, but what actually survives the long conversation between human ambition and planetary patience, and that true wisdom might lie not in building monuments that will last forever, but in living with sufficient grace and humility that the memories we leave behind, however fragmentary, however misunderstood by future discoverers, might serve as gentle guidance for other consciousness that will someday face their own versions of the questions we have grappled with about how to live thoughtfully on a planet that is always changing, always challenging us to adapt, always teaching us that our home is not a stage for human drama, but a living system that enfolds us, shapes us, and will continue its ancient rhythms long after our brief song has faded into the deeper music of geological time.